Well, you were here this blustery afternoon, as Charlie said, to hear Bob Byer speak and not me. And so my task at this point is to give Bob the introduction that he deserves in the tersest manner possible. And I'll try to do that. Now, let me start by saying that I don't know whether Bert McMurtry is in the audience, but I don't actually regard him as my most distinguished PhD graduate. My most distinguished PhD graduate, I think, was Steve Harris, who, as you'll hear in a minute, was Bob Byer's PhD supervisor in turn. So I guess I'm the academic grandfather on this occasion. And I do want to say that I think that having kept Bob Byer on at Stanford as a faculty member is probably the best thing I ever did for Stanford University. He was a problem graduate student. Every time I gave him an idea for a thesis problem or a topic or something, he would come up with one that was 3 times better that he generated himself. In any event, with regard to Bob, I'll just start this introduction on one day in the late 1960s when Steve Harris called me from my office across the hall to his lab, which was right across the hall, and wanted to show me the light coming out from a laser beam passing through a so-called nonlinear crystal and generating a kind of spontaneous quantum parametric emission light, kind of light that I think had never been seen visibly by any other human beings. And of course, the graduate student who was in the lab at the same time was none other than Bob Byer, who had carried out this experiment. My memory is that this took place late in the evening, something like 11 in the evening, but that may be a romanticism that comes from the memories of old age. So within months then, Steve Harris, Bob, and Ken Oshman had made this spontaneous emission into a new kind of coherent optical parametric CW emission that is technically very important these days. And not long after that, Bob himself became a member of the Stanford faculty. Since then, he's had a very distinguished career as a researcher and teacher in lasers and optics. At Stanford, he's been, among other things, the associate dean of associate dean of H&S, and then the vice provost and dean of research. He's been the director of the Ginston Laboratory, the Hansen Experimental Physics Laboratory, and twice the chair of the Applied Physics Department. The number of awards that he's received are I think, more than you probably want to listen to, and the number of companies that he and his students laser companies have co-founded in the Silicon Valley area are more than I can keep track of. He is also a member of both the National Academy of Engineering and the National Academy of Sciences. And over the years, he's been president in succession, first of the IEEE section devoted to lasers and optics, now called the Photonics Society, then president of the Optical Society of America, and at the minute, he's the president-elect of the American Physical Society. So I'm very glad to introduce Bob, and I'm looking forward to hearing him speak again.
Thank you very much, Tony. The problem I face is to get this non-laser technology on this stage to work. So let me see if I can get my computer started and get it talking to the screen, and then I think we'll be in good shape. I'm glad you can't see my password. All right, that went quickly and smoothly. Good for us. So let me see. I brought 2 laser pointers along today just to make sure that a laser is going to work. Let me try this one. Can you see that? I can't. I can't see a thing on that one. I guess I put that one aside. That's not going to work. Let's try my other laser pointer. Can you see that? What color is that? I can see green. That's good. All right, let's start with that one. I can't see red, and so I had to invent a green laser pointer so I could actually give talks like this. All right. So, lasers at 50. I didn't know what a laser was the year they were invented. I had no clue. And it's actually quite extraordinary to think back over the 50 years of time, a great many of them here at Stanford University. So I'm going to try something slightly complicated today, and that's to give you an idea of sort of the early history, sort of prior to lasers. We call those microwaves. And then bring you up to the laser invention itself and a little bit of the work that went on here at Stanford. And then I'm going to move and give you examples of some applications of lasers, particularly in science, and a little bit of applications at the very end that reach beyond that. And then finally do a little bit of blue sky stuff and talk about what might come down the future. If you think about it a little bit, 50 years is actually a short time in the history of a technology. If you look at my favorite science magazine called Forbes Business Magazine, they have a very good science editor, and he once looked at how long it takes a technology to be integrated into society broadly. And it turns out 100 years is what it took electricity to be integrated. It took aircraft about 100 years, highways and automobiles about that time. Electronic components, after the power supplies were built, only took about 50 years to be integrated, and lasers took about 35 before they were widely used by virtually everyone. So, but we have a long way to go, and I'll try to give you an idea what some of those future applications are that look really interesting. All right, now, I was quite frightened when Tony asked me to come and give this talk because I have a very high regard for those that are historians and do the real work that historians do. But fortunately, I was saved by the comics this Sunday. And so this non-sequitur comic, the bottom line is, well, the caveman and the cave woman are all complaining. She says, you didn't go to the bank this weekend. He says, I got so busy I forgot. She says, what are we going to do? You don't have money, so you can't take me out to a movie and dinner. Movies haven't been invented yet, dear. That doesn't matter. And that's when the ATM machine came along and changed the world. History is much more interesting when you edit it. All right, so I'm going to edit history. That's when the laser came along and changed the world, and we're going to edit it. And so my version of history is just that. It's my version of history of the laser over the last 50 years. We are celebrating Laser Fest this year, and this is now an international celebration, much more, it took off and became big, much bigger than most of us imagined it would. So all of the major scientific societies around the world are sponsoring this. These are the view of laser scientists who are there at the beginning, and I've been to Germany 3 times already this year, China, Berkeley. The travel is going to be heavy for those of us who have been around long enough to have been around somewhere near the beginning of the laser era. So I invite you to go on the World Wide Web, type in Laser Fest, and you'll get a list of the talks in your area and a copy of those talks that have been given already around the world. I'm going to start with this slide of Charlie Towns. Charlie is my sort of academic and hero in many ways. He was there at the beginning. It was his seminal idea that allowed masers and then lasers to come along. And I'm going to use as my theme light waves and talk in the prelude from radio and microwaves, and then we'll talk about making light waves and finally writing light waves. And then in the very end, we're going to take off into the future that none of us can see, and I'll call that surfing light waves. So that's the agenda for a conversation. Now, sometimes you get surprised by the simplest things, and this is a book written by Mary Fox, and this was actually written for young girls to interest them in science. So I put an introduction to lasers written for prospective scientists, young girls and boys. And on the side here, you see the color spectrum. Now, we know the red, green, and blue are the visible spectrum, but way down here is radio waves, here's microwaves, Stanford had a lot to do in that era. And then up here is X-rays and then gamma rays. And before the end of this talk, I'm going to try to persuade you that in 100 years, we've marched from that end, 1900 as radio waves, all the way up to X-rays, and we're on our way toward gamma rays. That is, we make coherent light across this very broad frequency range of the spectrum. What I like about this book is it's extremely accurate. It's an amazingly accurate book. It says laser light is made up of a collection of identical photons, each exactly the same as the other. What a statement. That's exactly right. Lasers are special. Photons like each other. They cohere and they stay together, and it allows us to make this wonderful tool. So in this book, I also like it because there's a picture. And it says this young man here is a student at Stanford University in 1968. He adjusts the crystal, the lens, the mirror system of the first laser to generate continuous visible laser light at varying wavelengths. Steve Harris, who is this young man? All right, that's a young 26-year-old Bob Byer in the laboratories here at Stanford University, just having successfully generated red light that made his thesis project successful. And so I like books that go out to young men and women that have pictures in it of a young me. So if I take that frequency spectrum and I turn it on its side, so this is radio waves and that's gamma rays now, I can now plot the progress of mankind's inventions in coherent radiation sources. And we start with the radio in the 1900s. In fact, by 1930, there were 30 million radios in use in the United States by 1930. 1960 was the year of the laser. Microwaves. I can't forget microwaves in the late 30s. The laser, 1960. X-rays, 2009, last year. The first coherent, truly coherent X-ray laser built at Stanford University at SLAC in 2010. And I'm going to predict that in this plot, which is exponential versus year, that sometime in the coming decade or decade and a half, we'll actually make a transition to a new kind of coherent source called gamma rays. That means radiation from the nuclei of atoms will actually be coherent, and we can use it for many things. So Livingston plots are plots of innovation. They're plots of being smarter and learning new ways to do things. Well, Stanford started not with the laser, but actually had a role to play in the early radio days and a very significant role to play in the microwave days. And for those of you in this society who have not yet read the book, The Inventor and the Pilot by Dorothy Varian, I highly recommend it. It's a very fascinating story of the Varian brothers, why they were motivated to build a thing called a klystron that generated microwaves. And the motivation comes from this image of Sieg Varian, who was an airplane pilot, who had to fly airplanes from Los Angeles to Mexico City. Not bad, except he flew by visual flight rules only. So when you came over the high mountains around Mexico City and you were up in the clouds, you had to carefully pick your way down through the clouds not to hit the mountains around Mexico City. There was a need for radar. So the Varian brothers worked on that. They discovered and invented the klystron tube, and that is the source of microwave radiation still used today in the aircraft that we fly. That same klystron is the driver for another invention called the linear accelerator. And the first electron accelerator at Stanford was built by W.W. Hansen. We named a laboratory after him. And this 1 meter long accelerator was the very beginning of the eventual SLAC accelerator up on the hill. So accelerators are going to be part of this talk. This is what an early accelerator looks like. You'll notice the names W.K.H. Panofsky, Pief Panofsky, and Bob Hofstadter, who won a Nobel Prize using this tool to explore the nuclei of atoms. I like the fact that when the accelerator actually worked for the first time, Bill Hansen wrote a report to the Office of Naval Research. And his total final report, the entire report consisted of the words, "We have accelerated electrons, period." Ed Ginston is perhaps my great-grandfather in the academic sense. Ed had the foresight to imagine that we might have a need for an applied physics department at Stanford. He understood that research at Stanford involved more than one department and more than one school. And so this photograph shows Ed in his later years in the photography lab, a klystron which he helped develop that powered SLAC, and a photograph of the Ginston Laboratory Courtyard, a place where all of us spend a great deal of our time learning about science from each other. You probably can't read it, but it says, a gift. This wing of the microwave lab, which is what it used to be called, was made possible by a gift from Very and Associates, 1956. So the lab that we are in now was created in 1956, and we will move from this laboratory in 2 months, in July, into a new building that's next door. Most of us dread the move. We love the grand old dame called the Ginston Lab. It's been extremely good to us for the last 50 years. The Varian brothers, Marvin Chodorow, he was my academic advisor in the applied physics department. The klystron, they all played a role of coherent radiation in the microwave range at Stanford, and they laid the groundwork for light waves. So, if you're going to build a small accelerator, maybe you'd like to build a monster accelerator to do new kinds of physics. And it was Ed Ginston who carried that story back to Congress and had to ask Congress for the money to enable the development of the Stanford Linear Accelerator Center. Someday I think it's going to be called the Stanford Laser Accelerator Center, but we'll see. So SLAC was started in the early 60s. First beam was seen in 1966, and it's been a smashing success ever since. All started with a device called a klystron. Now, we got to get serious here. I have to do a little operation here and hit function F7, and I got to hit function F7 again, and then, come on, then I got to go forward one. Yes, are you there? Now I've got to find my laser pointer. There we go. This is real serious business. This is Stanford at its best. Here we go.
When the arts and sciences demand innovation, the people at Stanford University answer the call. That's no more apparent than in their contributions to the study of energy waves. By creating a klystron tube, Stanford researchers harnessed an energy with more potential than anything that came before, an energy known today as the microwave. Hail, Stanford, hail.
Do you want to see that again? You asked for it. Listen carefully. This has a lot to do.
When the arts and sciences demand innovation, the people at Stanford University answer the call. That's no more apparent than in their contributions to the study of energy waves. By creating a klystron tube, Stanford researchers harnessed an energy with more potential than anything that came before, an energy known today as the microwave. Hail, Stanford, hail.
All right, good. You got that, right? All right, microwaves, and we're going to come back to accelerators at the end of this talk because we're right at the threshold now of moving forward with different approaches to making accelerators, a really important tool for physics. Let's move on to lasers and making light waves. But I'll remind you that California not only has been first in aerospace technologies, but led the world in telescopes for more than 100 years, and in fact is still leading the world in advanced telescopes, which use all of the optical components that we understand and know about lasers. And this is what got me in science. My grandfather worked on the Mount Palomar telescope and the Mount Wilson telescopes, and because he was the chief machinist of the machine shop, he had free keys, free access to these telescopes, not only just to look at them, but to walk on the floor and talk to the astronomers. So as a young man, I decided I wanted nothing more than to become an astronomer. And on my way to the University of California at Berkeley, notice I wore my gold tie, I had a chance to interview an astronomer at Caltech, Harold Babcock. And I said, you know, I'm going to go to Berkeley and I really want to be an astronomer. His first words were, "No, you don't, young man." I said, "What do you mean?" He says, "You want to major in physics, and if after you study physics and know a broad range of science and you want to study astronomy, then okay, you can study astronomy after that." I followed his advice and indeed joined the physics department when I arrived at Berkeley. All right, the maser concept had been invented by Charlie Towns about 6 years before that little story in 1951. And it's an elegant concept in which you use light to interact with molecules, in this case ammonia molecules, in order to gather energy from those ammonia molecules. And this very elegant concept forms the basis for all the lasers that we work with today. The instrument shown here, this is Charlie and his co-worker and student Jim Gordon, and the big vacuum system for this ammonia beam maser is at Columbia University. This is Model 2. I don't know why they never got a photograph of Model 1, but Charlie confirmed in Berkeley in January that this is indeed the second model of the the maser. All right, his co-worker, Art Shallow, and Charlie published a book on microwave spectroscopy in the mid-1950s. I call this From Radar to Fundamental Science. You will hear those words in a few minutes again. And so now we're in the laser era. Charlie and Art Shallow published a paper predicting that maybe we have an avenue for making a visible coherent light source. And that story is written in a book by Charlie again on how the laser happened, a delightful read. The page from the notebook is here. It's dated 1957. This was the genesis of how we go about building the coherent light sources that we know so well today. So this is my shortcut version. We'll talk about Ted Maiman in a second, and then I'll introduce you to a few lasers that Stanford had some things to do about or were developed here in Silicon Valley, not yet called Silicon Valley. And we'll walk through this sort of early phase of lasers. I made a point at the bottom of this slide that last year was quite a special year in lasers, and we'll cover each one of those topics as we go along. So let's start with Ted. Ted Maiman was a Stanford PhD student. Like Tony said, sometimes PhD students are a little bit onerous or difficult. Well, Maiman had done his undergraduate degree in electrical engineering. But when he arrived at Stanford, he wanted to study physics. But none of the physics faculty wanted him to study for them. So he had a real problem. Finally, it became the case that he could work on his work and lasers in the physics department. And he indeed got his physics PhD under Willis Lamb. He's shown here holding the first and original components of the Ruby laser, a very simple device, but he thought hard and long about all of the elements to make this laser work. And it worked the first time he assembled the components and tried them out. He was met immediately with a press conference hastily arranged by Hughes Research Labs in Malibu, California. See, here we are, California, a leader in lasers already. The press conference wasn't well thought out by his fellow people at Hughes, and so there was everything from death rays to horror weapons to light brighter than the sun in the newspaper articles around the world. There was even a lot of debate early on that his laser never really worked, and that debate has some echoes still ringing today. But those of us who knew what he did, understood how much thought he put into it, agreed that he demonstrated the first laser device ever seen in the world, and he did so at the Hughes Research Labs in Malibu, California. Art Shallow was at Bell Labs at that time, and in fact worked in the Bell Labs group to reproduce the Ruby laser experiment as quickly as they could. And then Art left Bell Labs, among many who did at that time, and came to Stanford. And he arrived at Stanford in 1962. He joined the Applied Physics Division of the Physics Department, and he joined the microwave laboratory. Now we call it the Ginston Laboratory. And when he won the Nobel Prize in 1985, it was quite interesting because the first words he said to his colleagues in the physics department were, "I'm really pleased that the Applied Physics Department invited me to come to Stanford University." And that blew the minds of my colleagues in the physics department who had never realized that Art had joined the Applied Physics Division in the Ginston Lab. This shows his Ruby laser, but it's not my favorite picture. My favorite picture is this one. This gives an idea of who Art really was. He had a great sense of humor. He had a way of dealing with science in an intuitive way that was really right on the money. So I made two Art sort of quotes here. If I had set out to invent a method of reattaching the retina, I would not have invented the laser. Think about that for a minute. He knew that if he had a laser, he could do a medical operation that was impossible to do at that time. That is, be able to either close blood vessels or reattach the retina on the back of your eye. The laser eraser. The laser eraser may not find any near-term application, but it is interesting. Well, there's an example at the bottom of a laser eraser erasing print off of paper without damaging the paper. This is the basis for about 80% of the applications of lasers. We use lasers to remove paint from aircraft. We use lasers to remove material from silicon circuits. We use lasers to remove and drill holes in circuit boards. Every piece of electronics that you carry in your pocket today, every cell phone in the world is made with a laser and could not be made otherwise. So Art had a far-seeing way of thinking about science and applications of lasers. Oh, what is he doing here? He is using a laser to pop a balloon, Mickey Mouse balloon, inside of a clear balloon, an analog to light going in your eye. But the secret of this experiment wasn't the laser he used, it was he bought the balloons at the San Francisco Zoo, and the real secret is he had enough breath power, lung power, to blow up, inflate that blue balloon inside the white one before he did the experiment. I took my wife to see Art do this experiment one evening over at SRI, and Art set it all up and it was all ready, and we were sitting in the front row, and Art gets out his ruby laser, and it takes a minute to charge up, and he walks over to the balloon, pulls the trigger, and nothing happens. And he sits there, wait a minute, I'll recharge the laser again. Recharges the ruby laser, pulls the trigger, and nothing happens. He reaches in his coat pocket, pulls out a pin, and pops both balloons. So my wife, to this day, never got to see Art use his laser to pop the balloon. Art edited a set of articles in Scientific American that bridged the pre-laser days to the laser days. And I just dug this book out of my office file. I was quite amazed because it gives you a view of the world from before the laser was invented until after, when you saw this kind of pattern on the wall. And the laser that made that kind of pattern is a helium neon laser. The first one built at Bell Telephone Labs by Ali Javon, Bennett, and Harriet. The first one didn't operate in the visible, it operated in the infrared, but nonetheless, it was a real tour de force. This laser is a difficult laser to build and operate. So I challenge my students every year in the laser laboratory I teach, when they build a helium neon laser, to reproduce this experiment. Put a pair of flat mirrors on the laser, make sure that everything is aligned. Oh, by the way, don't use a laser to align a laser, but use your eyeball and an autocollimator. It takes about an hour to do that. And to this day, they have yet to be successful in making this kind of laser work in the conditions that this team got this laser to work. Quite an amazing feat. The helium neon laser underwent technical development rather quickly, and the red line was discovered, the red line that you and I all know about. And this is a photograph of a Hughes Research Lab, Bill Bridges. Here's the first commercial product made by Spectrophysics Perkin-Elmer, a local company located in Mountain View, California, and founded in 1962. And here's the 1/1,000,000th laser made by Uniphase. So you go from a few lasers in 1962 to 30 years later, you make 1,000,000 lasers. Where was I in 1962? I was at Berkeley studying physics, and I was working in my spare time in the lab of Professor Sumner P. Davis. And that meant that I was doing optics research and spectroscopy research, but nobody mentioned the word laser to an undergraduate student who was sort of clueless at the time. My academic advisor advised me that I should get out of the optics field. There was nothing going on there. It had all been invented in the 30s, and I should come to him with him to Australia and study cosmic rays. Fortunately, I loved light, and I decided to stay and continue to work with light. When I graduated in 1964, Sumner Davis suggested I go down to Mountain View, California. I'd never been there, and visit a small company. They might have a position for someone like me. So I went down and I met this man called Earl Bell. And it took me a while actually to get in the door to say hello to Earl, because he had just made another visible laser work. And I was so excited to see this thing called a laser. I called my fiance and told her that I was not taking the job in Pasadena that summer. I was going to stay up in Mountain View, and if she wanted to finish her 4-year degree at the University of California, she was going to have to move from UCLA to Berkeley. That didn't make friends, I'll tell you. So I worked for a year at Spectrophysics. During that year, Bill Bridges and Labuda and Gordon at Bell Labs and Bill Bridges at Hughes invented the argon ion laser, this great big 1-watt blue-green source that we used in all the laser light shows for 30 years. The laser beams became powerful enough to do really interesting work. You see names of companies, Spectrophysics, Uniphase. Bell Labs was always there because Bell Labs was the place you went to do the best research in the world. So here's my brief little story about companies, and I can't possibly include them all, but these have some Stanford connections. Herb Dwight, CEO of Spectrophysics, founded in 1962, with Bob Rempel, Kem Ruddick, Earl Bell, and Arnold Bloom. They all came out of Varian Associates and the Klystron developers. Chromatics was a spin-out of Spectrophysics in '69. Steve Harris was involved in that company because it commercialized the tunable laser sources. Coherent split out from Spectrophysics in '66, and for 20 years, Spectrophysics and Coherent battled each other with legal lawsuits going back and forth on who owned what technology. '74, a company called Quantaray, partly out of Coherent, partly out of Spectrophysics, commercialized some neodymium YAG technology. And Bruce McCall is here this evening, and he founded Molectron, and he told me before the talk, 1969, so I need to remember that. All right, here's an image of Herb Dwight. Herb is a tireless worker on behalf of Stanford University, and in 2007 received the Gold Spike Award from the university in recognition of all of his efforts. For those of us who knew him with his business hat on, he was absolutely a first-rate individual on a board of directors or recommending directions for your company. The Coherent was founded by Jim Hobart and Gene Watson, and they located their company in the Stanford Industrial Park just across from Page Mill. Gene Watson is now retired up in the Dakotas area, and I haven't seen Jim for quite a while, but he ran Coherent for a number of years, a very successful laser company. I can't go by this without introducing Al Hildebrand. He's a good friend to many of us here. While he was at Spectrophysics, he was given the problem, the challenge of developing the supermarket checkout scanner using the laser beam. And so Al took that on, and in fact, that was the most successful commercial product out of Spectrophysics. A way to say it is 30 years later, sort of the anniversary of the supermarket scanner, people around the world use the supermarket scanner more than 1 billion times each day. This indeed has changed our lives forever on this very simple but elegant way to solve a problem. Earl Bell became my mentor at Spectrophysics. He taught me how to invent. That's an interesting skill to learn. It can be learned. We worked on argon lasers, we worked on helium neon lasers, we worked on making lasers commercial products, and I learned how very difficult it was to take an idea in a research lab and turn it into a well-functioning commercial product. Earl said that someday if a laser can operate at 5% efficiency, it can do real work. Well, that someday took about 30 years to happen, but I'll give you examples a little later of a laser doing real work. Tony Siegman, this is for you. That is Tony Siegman right there, on this side, right there. I'm guessing, Tony, this was 1974 when Lotokov visited. Pretty close to that, right? Lotokov was from Russia, a laser spectroscopist, very interesting gentleman, nice to have come and visit Stanford. Tony ran a brown bag lunch at Ginston Lab, and I learned about it while I was at Spectrophysics. So I asked my boss, Herb Dwight, could I go up and go on Wednesday noons to these brown bag lunches? And his answer was, yeah, you can do so if you make up the lost time from taking off work. So I went up and joined, and I got to meet graduate students there. And one of those students was John Bjorkholm, a Tony Siegman graduate student, and a very successful career in nonlinear optics and lasers at Bell Labs, and then retired back here in California. So you're looking much better in this picture, Tony. Steve Harris. I applied to go to graduate school, and for some miracle that I never quite understand, I was accepted at Stanford. And in those days, you were assigned to a professor, and I was assigned to be a student with young Steve Harris, an assistant professor at that time. I can't go by without bringing this up to date, so that's a much better picture, Steve. This one does you justice. We worked on tunable lasers, nonlinear optics. Ken Oshman was a co-student, Larry Osterink, Jim Young, Dick Wallace, so they're really a great group to work with. Problems were almost impossible, but not quite, so we could actually make progress. A great deal of a good time in that lab. So here's the first experiment, the thesis experiment. It worked on May 11th, 1968. The margin for success was measured in a few milliwatts. This experiment almost didn't happen. You need a little luck in your life, and this one we had a little luck. So we had a tunable red output that is a tunable or visible laser, which was quite a challenge at that time. It was commercialized in a company called Chromatics, and started in about 1970, and this is a young Richard Wallace. Dick and I still play golf together on early mornings at the Stanford golf course, and he's still healthy and plays a mean game of golf. All right, so now we've been through the early days. Let's go on and look at some of the more recent applications of lasers and what they mean for us. And I'm not going to pick on applications that are commercial market ones. I'll pick on sort of science things. Why is that? Most of our work at Stanford in lasers has been motivated by science. That is, the scientific demands placed on lasers mean we have to invent new ways to build lasers. And we do them because we want to do something important and contribute to science. So I like the Win Land quote from 1982, another of my famous science magazines called Business Week. Don't undertake a project unless it's manifestly important and nearly impossible. Now, your graduate students don't know those last two words. They just know it's important because you told them it is. But what you try to do, of course, is pick a problem that's so hard that they can just get over the hill and get it done, and then it might be important. So we picked on remote sensing. We had a tunable laser source. That's what we had invented. And we began to look at the idea of applying it to measure molecules in the atmosphere, and that we did. My first graduate student was Helge Kildal, a student from Norway. He's back in Norway and retired at this point. So monitoring air pollution with lasers was a good subject. In fact, it became an international subject, and for the first time I began to have the opportunity to travel to Japan and work with Humio Inaba, travel to Germany and work with Herbert Walter, travel to Sweden and work with Sune Svanberg. So now the world took on a completely different form. You could travel around the world to do your science. So laser remote sensing was a hot topic at the time. It turned out it was a very hot topic 2 weeks ago in Europe. Why was that? Because there was volcanic dust over the airports, and the airports had been closed, and no one knew how to measure how much dust was really there. These lasers were used to make that measurement before airplanes were flown into the dust to take samples. So we made a tunable computer-controlled laser. This was the first computer-tuned laser that I know about in the world, with a PDP-8 computer with 8K of core memory. 8K of core memory, think about that for those of you who have cell phones in your pocket. All right, transmitted the light through a telescope on the roof of our lab when we measured the air pollution across the bay. And to our surprise, we found that methane in the bay was a factor of 2 higher in concentration than on the global average. It took us quite a while to figure out it was all the dumps along the bay that were emitting the methane that brought the methane level up in the bay. All right, Tony Siegman invented a new kind of resonator. He named it the unstable resonator. That sounds like it's all shaky and things. He doesn't mean that. It means it's stable mechanically, but the optical rays diverge as they go out of the resonator. And it turned out that people had tried to build lasers using this idea, but had been unsuccessful. It's always good when you're going to apply for a patent if you can find a paragraph in a textbook that says, we tried this and we're unable to make it work. We don't think it's possible. When that sentence appears in print, go to the patent office. You've got a good case. So we tried the idea. It worked. We used it to make very high-power neodymium YAG lasers, and those YAG lasers were what drove our air pollution remote sensing measurements. That got transferred to a company called Quantaray, and the company called Quantaray, when we first started it, I figured Quantaray might sell 75 lasers in the whole world. That's all I could imagine. And in mid-1990s, I asked the CEO of the company how many Quantaray lasers had been sold, and more than 10,000 of these lasers have been sold around the world. Quite amazing. There's a celebration here in 1975 to 1984 when this company was sold to Spectrophysics. So what comes next? In the company frame, what came next was a 2-year non-compete agreement. You can't go into anything. So That's what comes next. Well, you go back to the research and think about what's important in research. I bring up this because Milton Huffaker had a dream in his life, and his dream was someday to fly a laser in space on a satellite and use that laser with coherent Doppler radar to measure winds, to measure the wind field on a global scale. This problem still has not been solved. So this is one of those nearly impossible problems that's still on the impossible side of nearly impossible. It should be solved because it's an important measurement to make on a global scale. So what it did was to get us thinking about what kind of laser should you invent and build to fly on a satellite. It needs to be small, it needs to be efficient, it needs to have long life. And because of that challenge, we began to work on an idea to use a laser diode, the same diode you use in your red laser pointer. So this is a laser diode pointer that I can't see. We use the red light from the diode to pump a neodymium YAG crystal to make a new kind of laser, a diode pump solid state laser. So our first laser had all of the power of this laser pointer, that much power, a milliwatt, not very much power at all. And it didn't look like it might be all that promising, but it was relatively efficient. So we went on to build a laser coherent radar. This sounds like microwaves all over again. We invented the local oscillator, which is this small little chip of crystal of neodymium YAG, extremely narrow line width, extremely stable laser. In fact, it's so stable that 30 of these lasers are used in every US submarine today to detect sound waves in the ocean. So this laser has found widespread application because it's extremely narrow line width. All right, at the same time, my students asked the question, well, we have a 1 micron laser, can we double it and make it green? After all, that's what I learned how to do working with Steve Harris. So here we go. Bloombergen was the first to really pursue nonlinear optics seriously. In Stanford, we were also doing research on converting the color of a laser to a different color. And today, if you go to Fry's, you can see that this idea has made it big time. Mitsubishi has introduced a laser-driven television set, right? Using nonlinear optics to make this color of green to light up your television at the green light. And it's about twice as electrically efficient as the best LED laser. So it's a more efficient laser, and the colors are spectacular. So if you want to see a laser television, go down to Fry's and look at the Mitsubishi variety. So the laser pointer came along at the same time. The laser pointer I like because it came from a question in class. People often ask, well, why are you teaching? Doesn't that get in the way of your research? The answer is no, it doesn't. Students are smart. They're going to test you. So in one class in the morning, Jeff Dixon asked the question, you know, can I take this little infrared laser you built and turn it into a green laser? And my answer was, I don't know. You don't lie to Stanford students. They're too smart. So I didn't know, but I'll go do the calculations on the weekend. If you go do the calculations on the weekend, we can compare notes next week. We did. It looked like we could make a green laser by putting a little nonlinear chip inside the laser cavity, and that led to a thing called the green laser pointer. Stanford got the patent. Really neat. The patent ran its course and matured before the market for the green laser pointer took off. Right, John? John Sandelin is here. He handled the laser technology transfers out of the Office of Technology and Licensing for us for many years. But this is still my favorite invention. It's my favorite invention because I'm an amateur astronomer. And when we have kids come out to look at the sky at night, we use this to point out the stars. It's an absolutely fabulous way to give people a view of what's in the sky without waving your hands in the dark air. There are applications for the green laser pointer, and some of them are really fun. You realize green laser pointers are now approved for rescue flares for sailors at sea. They're waterproof, they've got batteries, they float, and if you're in a sailboat and you're lost at sea and you want help, I'd much rather have a 300 milliwatt green laser pointer lighting up the sky rather than shooting a flare off every once in a while. All right, so that means that I have to, good. So this is important. I've got to go back and do my trick again here. All right, come back. Uh-oh, I need to go there. Ooh, perfect.
The faculty at Stanford University continually develop world-changing ideas across all disciplines, among them the laser. This cutting-edge creation harnessed the power of light and has since helped advance everything from modern medicine to manufacturing. And even now, over 40 years later, the laser's full potential has yet to be realized. Hail, Stanford, hail.
Hail, Stanford, hail! All right, so that's a characteristic of Stanford. We all have a little bit of disbelief about anything we hear and do at this university, and I think that's a good illustration of what a green laser pointer is really useful for. All right, companies. So at that same time, we had companies coming along. Lightwave Electronics was formed to commercialize the diode pump solid-state laser. A very good friend and still a good friend, Bob Mortensen, became the CEO. Tom Kenan and Dick Wallace joined that company. Milton Huffaker, who really had the dream of doing lasers for wind sensing, formed a company in Boulder, Colorado called Coherent Technologies. Milton Chang moved from Newport Beach, California, and moved up to Northern California to be where the action is in lasers, and started a company called New Focus. Spectra Diode Labs, Don Cyphers, made diode lasers with Ralph Jacobs and David Welch. You get an idea that the 10 years after the invention, 20 years after the invention of the laser, things are beginning to bloom. There's a lot of activity going on, including the activity at the national labs, which I list across the bottom. This will be my last slide on sort of companies, because if I showed the next one, the whole sheet would be filled with names as companies bloomed. Here's Tom Kenan and Bob Mortensen, and Milton Chang, who was on the board of Lightwave for a while before he started his own company. Every one of these companies also made cups like this, so I was thinking of just lining up all my mugs and taking a photograph, and it would tell you about all the companies in the Bay Area. John Willison, a Steve Harris student, started a company that makes precise instruments called Stanford Research Systems. Kurt Weingarten and Ursi Keller, they met in the Ginston Lab and are a Ginston Lab couple. Got married and moved to Switzerland, where Ursi's a professor at ATH, and they started a company called Time Bandwidth Products, another successful company. You get the idea. The most important thing, though, is we had help. And one form of that help was the Office of Technology and Licensing. And Niels Reimers, who founded that office, had a different idea of what a technology licensing office should be. His idea, it should not be there to protect technology. It shouldn't be lawyers telling you what you can't do. It should be an organization to help facilitate the moving of these ideas into the commercial stream. So his 3 words were, our Office of Technology and Licensing is based on one thing: marketing, marketing, and marketing. So we had a good time working with Niels. I first met him in 1969 when his office was in a trailer near Encina Hall. This photograph was taken a few years ago with Myron Kleinbard, who helped to take one of the most successful patents at Stanford and turn it into a real moneymaker for both Stanford and for the company that he represented. We had a celebration in 2005 with Pat Devaney and Kathy Koo. Kathy became the director of the Office of Technology and Licensing, and the celebration was a milestone for that office. It had crossed the $1 billion income mark in November 1st, 2005. So quite an important organization for all of us in technology transfer. This is the people that do that transfer. So last Monday, we held a reunion of all of the laser and optical and photon scientists that have ever been through Ginston Lab and graduated from Ginston Lab. My assistant, Vivian Drew, told me that there were about 500 names on that original list, and about 200 of our former graduates came back to the Ginston Lab. And sitting right there is Steve Harris and Bob Byer next to him, and Dick Wallace. I can name them all. They're an extended family, and they've been an extremely productive group of scientists and engineers. Now, science. I have to be careful of time. In fact, I might have to, I'll cut a few things out because I think we're going to run out of time. Okay, so one thing leads to another. What does that mean? That means when you do basic research, you don't quite know where the next step is going to take you. And in this case, the next step was, remember I said global remote sensing took us to diode pump solid state lasers? Well, it turns out the next meeting I bumped into somebody. The somebody was Peter Bender, a professor at University of Colorado, and he dragged me down to his basement. He said, I've got to show you this really neat science mission, this thing. And that thing was called LISA, Laser in Space Antenna. Its goal is to detect gravitational waves. You don't know what they are. I'll explain them in a minute. 1988. This is not just any interferometer. This is an interferometer with a 1,000,000-kilometer path length, and it orbits the sun 20 degrees behind the Earth. This is quite an extraordinary experiment. So Peter asked me, can you provide me the laser that I need by the time we launch this mission? I said, well, when are you going to launch? He said, we're going to launch in 1998, 10 years from now. I said, I think we can provide the laser within 10 years. LISA still has yet to launch, and it's always 10 years in the future. So sometime around 2020, this mission actually might get off the ground. It's a very expensive mission. Its goal is really always ranked high, to detect gravitational waves to view the universe. So we didn't do LISA. What did we do? We started a ground-based observatory. Caltech, MIT, Stanford, all joined early on to build interferometers on the ground with 4 kilometers of length. That's longer than SLAC, which is a 3-kilometer long accelerator. 2 sites, one in Livingston, one in Hanford, and we were asked to provide the laser for this instrument. And we did that. The instrument was built from 95 until 2002, and we invested time and energy to make this work so that we could someday detect gravitational waves generated by massive black holes, generated by binary neutron stars. Gravitational waves are extremely weak, so to detect them is a very, very hard problem. It's now an international effort. Germany, Italy, and Australia, Japan. There are about 550 people around the world involved in the LIGO project. Gives you an idea of just the institutions that are working on this problem. So why is this so hard? Well, I've tried really for a long time to figure out a way to try to give you a sense about why gravitational waves are hard. First, what are they? What they are is the motion of space-time itself. So you have to think of space-time perhaps as a pond of water. And if you throw a pebble in that pond of water, you get this beautiful ripple of waves that separates out. The water itself doesn't move, it stays still, but the wave propagates. So space-time doesn't whiz by you, but the waves propagate through space-time at the velocity of light. So that's what we're trying to detect. Well, it turns out they're weak. No, they're incredibly weak. No, they're worse than that. They're extremely weak. They're weak to a part in 10 to the 21. So I'm going to give you an idea of how small a part in 10 to the 21 is. You'd have a hard time on this. That's a lot of zeros. So the nearest star from our sun is Alpha Centauri, 4.4 light years away. That's a long way. 4 times 10 to the 16 meters away. So if I'm going to detect gravitational waves from Alpha Centauri, I have to detect motion to the diameter of the human hair, 40 microns, at a distance of Alpha Centauri. Space doesn't stretch very much, but it does stretch. Einstein taught us that, and he's right. So our goal is to discover these waves and make these measurements, and that means we have to make the most precise measurements mankind has ever attempted. There are a lot of sources of gravitational waves. We know that now better than we did when we started. Astronomers have been very helpful in identifying the sources of gravitational waves using optical waves as their signature. So the problem we're going to face is our signal is buried in our noise, and so we have to figure out a way to dig the signal out of all this noise. So I'll give you an idea of what this machine looks like. First, we have sensitivity curves. Most of you that are non-scientists won't be interested in that, but the sensitivity is almost good enough to see gravitational waves. We need to improve it a little bit. We're working on that now. We finished the 5th science run in 2006. We're now installing the advanced LIGO machine. It'll be finished in a couple of years. And sometime by the end of this decade, we should see the first gravitational waves directly in this observatory. So that's from initial LIGO to advanced LIGO, a lot of work to be done. Here's what it looks like on the ground. It's 4 kilometers of ultra-high vacuum. You see it here. And here's the crossover where the interferometers sit. What's this funny thing right there? That's a 6-inch thick concrete shield. Why did we have to put a concrete shield around it? Hunters shoot at anything that doesn't move. So if this were out in the middle of the desert in Hanford where it is, and somebody's out hunting and they saw this tube just sitting there in daylight, they'd shoot a hole through it. So we have to put protection up to protect the tube. Well, that protection has been tested. We don't know how this happened, but the driver lost control of his Jeep It rolled down the embankment and crashed into the concrete. It did not rupture the vacuum system. So LIGO consists of elegant set of mirrors on suspension to isolate from ground-based noise. Stanford invented all of the suspension system that's now being installed in LIGO. And we have the super mirrors, super polished, just elegantly beautiful optics to try to see these gravitational waves. And my colleague in Germany, Benno Wilke, has been working on the laser. The German laser was chosen for the advanced LIGO, and it's a very well-developed and very nice laser system that will actually be installed in the near future. So there's every reason to believe that advanced LIGO will see gravitational waves for the first time sometime in the next 5 to 6 years. It will open up a completely new window on the universe because gravitational waves are not scattered, they're not absorbed, they're not deflected. It gives you a view back in time all the way to the beginning of time at 10 to the minus 31 seconds after the Big Bang, when gravitational waves were formed by the quantum fluctuations of a hot, small universe. Future directions. I have a few minutes. I'll give you a little bit of idea of future directions. I was going to talk about what might interest everybody. Do we have a pathway to build the ray gun that shoots airplanes out of the sky? Cutting metal at a distance is what I call it. So I'll give you a little bit on that and maybe talk about laser fusion. All right. Going where no laser has gone before. For those of us who grew up on Star Trek, here you go. You know, it's a phaser, a laser, a photon torpedo. We know all the words. Do they actually exist in reality would be the question. Well, high-power lasers have existed now for more than 20 years, but they've not been small enough, portable enough, nor efficient enough to use in any real way. They can be used for cutting and welding and machining because those require 20 kilowatt lasers. These rays require megawatt lasers, and we don't have those in an affordable way yet. But let's go back to that very first 1 milliwatt laser, this little diode pump solid state laser in 1984, and ask the question, how did we progress from 2 milliwatts in 1984 to 1/10 of a megawatt in 2009? Wow, 2 milliwatts to 100 kilowatts in that short of a time frame. Well, a lot depended on this young man, Don Cyphres, who was a researcher at the Palo Alto Research Park, Xerox PARC, and he formed a company between Spectrophysics and Xerox PARC with the help of Herbert Dwight again, and the company was called SDL, Spectrodiode Labs, and they built diode lasers. And they began to make improvements on diode laser technology because this is a semiconductor technology. And a semiconductor technology can be looked at as Moore's law. As I build more of these devices, I get better. As the market grows, I have more volume, and that combination leads to a cost decrease in the lasers. And the cost decrease fell from 10 to the fifth dollars, yes, that's more than a Porsche cost for one of these diode bars in 1986, down to about $1 per watt today. So this continuous price decrease is because the volume of lasers used in the world is continuously increasing. And they're used for all of the manufacturing processes you can imagine. Because of that, and because of some nice innovations along the way, like slab laser technology, we built diode pump slab laser technology, and our work at Stanford wasn't aimed at making megawatt lasers. Our work at Stanford was driven by the LIGO project. We were trying to build a better laser to detect gravitational waves. And on the way, we accidentally bumped into a way of making very high average power lasers in a very simple way. And that technology got picked up, and it turned out it involved our friends in Japan to learn how to make ceramics that are transparent. You know ceramics because that's what your coffee cup is made out of, but you can actually make transparent ceramics for making lasers. And the one who convinced us of that was Professor Kenichi Ueda in Tokyo, Japan. So once we had these transparent ceramics, we have the materials to build high-power lasers. And the company I consulted for many years is Northrop Grumman, and they built this in-pumped YAG laser, which I'll describe briefly. It's based upon a ceramic of neodymium YAG pumped by diode lasers. So diode arrays are here. That's the gain element. And these are put together into an amplifier chain, and then they're melded together into a single laser beam using a lot of tricks called adaptive optics. So this laser was operated last year in January. The formal announcement of its success was made in March after it cleared all of the government clearances. And the laser is now down in New Mexico, attached to this transmitting telescope to begin to do field tests of a 100 kilowatt solid state laser shooting at objects in the sky. If you want to see what this laser can do, just go to your friendly YouTube and dial in the words high power laser defense, or laser defense high power laser, or high power laser. It doesn't matter what you put in. You will get to a video that shows the lasers easily bringing down helicopters and small airplanes, bringing down missiles that are incoming missiles, artillery shells, and multiple mortar shells in a row. So this technology is now still in its infancy, but it will not be long before your Star Wars image of a light beam delivered to a target is a reality. So 6 months ago, BBC television was in my lab, and they were hell-bent on trying to show that a laser was a weapon of mass destruction. That's the only words they wanted out of my mouth, no matter what. And so they kept baiting me, and I kept saying, no, a laser is exactly the opposite. It's a laser beam is a very precise beam. You have to point it exactly at what you want to hit, and the beam travels at Mach 300,000 and reaches the target and can do some damage. So it's exactly the opposite of a weapon of mass destruction. It's the kind of weapon if you need one, you'd like one that only does what you want it to do and no more. So this is my Livingston plot of power scaling and lasers. And it's a semi-log plot again, and the power goes up to a megawatt way up there. And it says by about 2015, we ought to see a 1 megawatt average power laser in the world. I have a bet with my colleague in the US Air Force on that. I'm going to lose the bet. It was a nickel bet. I put a nickel on the table. I always make nickel bets. That's your professional judgment. He made a bet of 2 slightly used aspirin. Not a very balanced bet. And I'm willing to lose the bet because along the way, 3 Air Force generals entered into this discussion and became quite disinterested in whether solid-state lasers were ever going to be bigger than just a laser pointer. They are now convinced they're going to be megawatt lasers in the future. Well, why would I be interested in megawatt lasers? I'm interested in science. My interest is laser accelerators. I would like to see SLAC, which is now driven by microwaves, be driven by lasers so that I can get more beam energy out of SLAC and more efficiency, and I can do more science in that beam. Another interest across the bay, again in California, is LIFE, a laser inertial fusion for energy generation. That is the laser fusion experiment going on at Livermore National Labs. So now, because of the time, I have a choice. We either talk about laser fusion, we talk about accelerators. How many want to hear about laser fusion? Raise your hand. Uh-oh, it's going to be close. How many want to hear about laser accelerators? I think accelerators win. Okay. That was too close for comfort, though. All right, I will talk about our work on laser accelerators. It's been a long, hard road to go, joint with SLAC, but we're getting close. Remember, I'm going to make predictions about the future, something that Yogi Berra said you shouldn't do. Okay, here we are. First LINAC 1946, Klystrons in the 1930s. On campus, we had an accelerator that we used for early experiments underneath the HEPA laboratory. SLAC was started in early 1960s, and we did the first laser electron accelerator experiment joint with SLAC from 1997 to 2004. Oh, by the way, along the way, John Mady demonstrated the first free electron laser right there with Dave Deacon and crew. And so that was the first time an all-electron device made coherent light. So SLAC, you can see the future of particle accelerators as predicted by my particle physics colleagues is we're going to do more of the same. We're going to build another SLAC, but 10 times longer to do the next generation of physics. That doesn't work. It turns out you can't afford to do that. You need to be smart, not be linear scaling. And so smart means you need a new way to do accelerators. So we began to look at the new way of doing accelerators a while ago. I actually began to think about this problem in 1974 when I was on sabbatical leave in Lund, Sweden. In 1994, I gave a talk at the SLAC Summer School on laser accelerators, and 2 years later, we formed a joint effort with SLAC. And in 2004, we had our first successful experiment. Sometimes science takes a long time. You have to be persistent. So I like this one because Pete Panofsky, the grandfather, the father, the godfather of accelerators. An accelerator is just a transformer. You start with power out of the wall and you cycle it up to very high voltage. All accelerators operate at the damage limit. You know, the converse of that is all lasers operate above the damage limit. They damage themselves. So anyway, it's a lot of fun to learn a new technology. It's certainly a lot of fun to be invited into a field that you're not an expert in by experts. And these are the experts in the field, the late Bob Seaman, Jim Spencer, Eric Colby at SLAC. We've had graduate students on this project, and our goal was to show that we could accelerate electrons with a laser beam. The PhD student was Thomas Pletner, a citizen of Mexico City in Mexico, and he was motivated to find a way to do this nearly impossible problem. He found neat tricks to play to be successful, and he was. And his thesis was completed with a successful demonstration. And so unlike the W.W. Hansen report where he said, we have accelerated electrons, we had to write, we have laser accelerated electrons. They had to put one more word in there. All right. We now are working on this joint with SLAC. We're using photonic crystal structures to make the accelerators. We're testing these at SLAC as I speak. So it's a difficult set of measurements to make on the SLAC site. But we have access to our relativistic electrons. We have access to SLAC's help, and we're making progress. This field went from being a dark horse to being an invited participant in the advanced accelerator research programs around the world. So we're now getting some headway, we're getting some purchase. I think there will be real progress coming decade. Our experiments at SLAC. So I'm going to end then on a note that we have accelerated electrons. We've bunched electrons to sub-femtosecond duration, quarter of a femtosecond or 250 attoseconds. And the PhD thesis a couple of years ago for Chris M. Sears was based on this topic. I like this photograph. It's Chris Sears graduating with a PhD from Stanford. His supervisor was Bob Seaman, the late Bob Seaman, and gives you an idea of what our most important product is at Stanford University, is educated students. All right, so now let me quickly go and say what happened in 2009 that you don't know about, you should know. What happened in 2009 is SLAC had a spectacular successful experiment to make the first coherent X-ray laser. Quite a remarkable achievement. The papers were submitted for publication on this laser a few months ago. Guess what? They were rejected. This is not new. Whenever you do something that's important and that big of a step forward, the reviewers who review often aren't up to date, and when they're not up to date, they don't believe you or they don't think it's important. This is a talk John Galida gave a year ago, September, at our annual meeting. LINAC Coherent Light Source, that's what it's called, SLAC's X-ray laser. And what it brings you is faster timing. It brings you resolution to sub-atom resolutions. Everything you can imagine you might want to do with an X-ray laser and then some, you can now begin to do. It builds on John Mady's invention and demonstration of the free electron laser in the 1970s. There are lots of free electron lasers operating around the world today. They're pretty big machines and they're pretty expensive. But at SLAC, using the linear accelerator, we've made it an exceptional laser that gives you very high spatial resolution, extremely good temporal resolution, and someday will allow us to image biological molecules in a single shot so that we can do the structure biology experiments. Here's what it looks like. It's an undulator. It's a magnetic field that wiggles the electrons. The electrons come from SLAC. There's a series of these undulators that span a distance of 100 meters. There's a lot of ways to make it stable: sand isolation, cavity feedback, beam position monitoring, quadrupole magnets for steering. This is a complicated, expensive experiment. But guess what? With all of this put together, it worked the first time, just like the Ruby laser did 50 years ago. So this is the image before you reach threshold. So this is spontaneous emission of X-ray light at 8 kilovolts of X-ray energy. And this is what happens 30 minutes later as you turn up the beam. So we're at 2103, 2133. Guess what? We have a laser. That is a laser beam, and it wiggles a little bit when you watch the movie, but it is an essentially very highly coherent X-ray laser. Incredible breakthrough. We now have to think about experiments and where the field goes for the next 50 years. Our research in my lab is to make that thing tabletop, but I'm going to skip that because there isn't time. So I'm also going to skip the idea of laser fusion and go to the last few slides because I need to go to the last few slides. So pardon my PowerPoint. Here we go. John Emmett, Stanford, director of Livermore, laser fusion, laser fusion. By the way, the laser fusion experiments will be attempted late this year, so keep your ears open. It will be a man in the moon event when laser fusion is demonstrated in the laboratory. We'll go from laser fusion to laser energy, called life. Someday, big lasers, high average power, they're being designed right now. We'll use diodes to pump for efficiency. We'll place a star on the surface of the Earth, a star we can control. It will turn on for about 10 picoseconds at a time at 5 hertz. This is an image I took last summer at the total eclipse of the sun in the South Pacific, just north of Tahiti. Beautiful sight to see in real time. I use it as my parting slide, saying if you want to understand the sun and you want to understand it in detail, you want to create it in the laboratory using laser inertial confinement fusion. All right, last year was a successful year. Here's the future. These are the students in the Ginston lab and electrical engineering, applied physics, physics, ME, all of the departments that use lasers, biology, chemistry, medicine. All of these students work with lasers in a research program. They hold an annual retreat. It's a great event to be invited to this annual retreat. Not every faculty member can go. You get invited by students. It's a lot of fun to go. I want to thank my family. It's not very often that you're blessed with a family that lets you pursue your passion for the amount of time that I've spent pursuing lasers and applications of lasers. And I'll remind those of you who love Hawaii as much as I do, tomorrow at noon I will be surfing waves at Poipu Beach, Hawaii. Thank you.
Is this on? Yeah. Thank you, Bob. That was spectacular. We're going to have you back and give you 3 or 4 hours to explain, to go through your slides more slowly and explain what you didn't have time to do. But this was exhilarating. Thank you. And because we would rather have listened to Bob talk than to our own questions, I think we ran late, and we have about 5 minutes for a few questions, and then I think we'll just have to adjourn. We will adjourn with pleasure to the reception, and you can ask your questions informally, and Bob will join us. But anybody want to ask a question over the microphone? Too shy? Yes? Okay.
So, Bob, you have 5 minutes to tell us about the inertial confinement.
So I have a 5-minute message. I've been a part of that project as a consultant, what I'll call pro bono consultant, for about 20 years. So I've watched the laser go through all the machinations and watched the Secretary of Energy come out and be embarrassed and claim that he was going to shut down this machine no matter what, and working really hard on the committee to turn him around. From the time in 1999 until the present, when Ed Moses took over the management of this machine, it's now successful. Last March, when I was in Israel, I received an email that the laser had been successfully commissioned. It had met and exceeded all of its specifications. This is really quite extraordinary. And so the laser is now shooting about 1 shot a day, 1 target shot a day. And it's not the laser that can't shoot faster, as it takes a long time to assemble and get the targets in place, get all the diagnostics up. They've run through a set of preliminary measurements. They are pristine. They're better than they would have ever expected. You remember, everybody predicted that it would never work. The laser would go into the plasma. You'd get stimulated Raman. You'd get all kinds of backlight in your face. You'd never get the light on the target. Wrong. The light goes on the target accelerates, it collapses, and you get full symmetric condensation of the target to a small point. That's a minor miracle that it happens so quickly. They've remodified the targets, upgraded them. This summer, they're going to do a set of target shots on the new target. And in the fall, late October into November and December, they will make the decision of whether to do a burn target, that is, put tritium in the target and make fusion in the laboratory. You don't do that lightly, because once you generate a megajoule of neutrons in 10 picoseconds, it puts a little bit of radioactivity around. You've got to wait 6 weeks to go back in and do another shot. So they want to make sure the first shot works, and they're doing all the physics measurements to ensure that that's the case. My guess, it'll be late this year, early next year, they will make the fusion burn shot. And everything that we know says they're about a factor of 2 above the projected thresholds. That's my eye candy, less brief summary.
Okay. I think, okay, one more.
I was disappointed not to see our son's name or hear it mentioned.
Oh, okay. What is your son's name?
David Bloom.
I'm sorry.
And
Oh, okay. So I have
he
pictures.
apparently is one of the more prolific inventors.
He is,
there.
and I had the name of his company, Silicon Light Machine, on one of the slides. I didn't take the time to go explain it. But David he was a student of Steve Harris. I know him very well. We actually traveled to Sony together 5 years ago to see the Sony World Fair display, the world's largest laser projection display, the size of a hockey field, 50 meters wide, 10 meters tall. David made the light modulator, we made the green laser, so Ginston Lab had 2 of the 3 technologies that made the world's largest laser projection display. So that was the last time we had a great time together visiting Sony in Tokyo. Thank you for mentioning that.
Do 3 things. First of all, I'm going to ask our president to close the meeting formally. Yes? All in favor? And thank you, meeting is closed, and invite everybody to the reception in the lobby out here, and let's finish with a big round of applause for Bob Byer.
Everything worked?